Parsa Mirhaji, as Alan had mentioned, was actually part of this Estes Park group, and I'm gonna call him one of the founding fathers that helped create the Data-Centric Manifesto. So this was a group that was collaborating, and still is a voluntary sign-up proxy that lives and breathes as a driving inspiration for the future of information management and the role that data should be playing in that. So it's just a pleasure to have Parsa join us. He's just a treat here. And as the director of health data innovations, he's been transforming how Montefiore Hospital in the Bronx is delivering improved patient care by leveraging data. So Parsa, it's your turn to showcase those highlights. Thank you.
Yes, thank you very much. I'm going to talk about our experience at Montefiore, and hopefully you will see fragments of a lot of the concepts that Alan and David talked about really combination of many strategies that creates a successful application for data-centric architecture and use of knowledge graph in this case in healthcare. So before we understand our take on our architecture, I would like to talk about the problem we're trying to solve. And because this is basically what everybody was talking throughout the day today, I'm going to just move fast. Everyone knows that in large organizations everywhere, like in healthcare, we have made millions of dollars of investments already on building these data integration constructs, enterprise data warehouses, clinical data warehouses, data lakes, and most institutions have more than one of these. But it's still the patient experience and clinician experience, what we see from really the results of this data is abysmal. We do not have an integrated healthcare. Healthcare is not an integrated enterprise. And the reason for that is that once we put the data in that enterprise data warehouse, we further fragment and create these analytic silos that individually they want to solve one specific problem. This is really like millions and millions of point solutions that a healthcare system will have to implement if they really want to digitally transform themselves, which is almost impossible. We have basically turned all of these data integration investments into bubble-making machines, silos that do not talk to each other. And one reason for that, if you look carefully, is our data architecture. This must be very familiar to everyone in this field. We extract data, transform, and load it into these data warehouses, these centralized repositories, these reference models that are built for specific applications. And every time we want to build an analytics or a software that will use this product, this integrated data set, we need another ETL to take a chunk of that data, put it in a completely different reference data model, add a few columns here and there to collect a little bit more data to be able to support that analytic. And frequently, we also need another hardware infrastructure just to run that analytic. And every application, every analytics, every software that we need to add becomes yet another one of these analytic silos that are really expensive to maintain. They are not really scalable. And how many of these pipelines an enterprise like healthcare can support? It's really not scalable. And the fact that you can put some of these infrastructure in cloud, although may scale that portion, it will really not make the overall architecture any different. You are still looking into this fragmented analysis environment where you don't have a full integrated picture of patient or your organization anywhere. So when we started designing our system, the question was how we can create a an integrated digital representation of patient that is universally available to all applications, to all analytics, current and future, and it is something that we can grow over time. Is scalable and resilient to change in time. And we can run all kinds of analytics on it, not just a couple of those things that we could come up with day one. So we designed this notion of patient-centered analytic learning machine as an indication of our desire to create this digital twin, this digital representation of our understanding of the patient that will evolve over time and will be shared across the entire analytic enterprise at Montefiore. So very quickly, let's see how we have done this. So our architecture is comprised of a extract and load process where we basically connect to the data sources that we need and load them into this what we call hyperstore, which is a big database based on it that is indexed by ontologies and semantic indices and is graph-based. It is really not aware, it is not specific to any specific software or any specific problem or any specific application that will run against this data. But it has a lot of metadata representing what the data meant at the source, how it was related at the source, and all of the provenance and security coordinates and characteristics of data is carried forward in this enterprise. All of the downstream analytics that we may run will have their own transformations on top of this data set to really transform data and cater to the analytics. But we don't stop here. What we do is that once an analytic is done, we return all of the results of that analysis, any byproduct of that analysis, any new insights generated by analysis, or that new software application back to the hyperstore. It is yet another data set. So every insight, every knowledge generated by all of the downstream analytics are basically forwarded back into this enterprise. And we have another graph-based technology, we call it Analytic Tapestry, that connects all of these insights generated by downstream analytics to the data sets and all of the original data inputs that were used to generate that insight and makes both analysis and the results of those analysis discoverable. It is very much like how a motherboard in a laptop or in a computer system connects all of the components of the machine and makes them discoverable. So as soon as you plug a USB drive or a camera or a microphone to your machine, it becomes discoverable by all applications. All applications will know that you have a new drive that they can save into, or you have a new mode of capturing or scanning information, and they can use it. This makes all of the analysis and all of the data discoverable to the system. This discoverability obviously requires a lot of data harmonization and data integration, so all of the analysis and software can understand each other's language. That's why we have a knowledge base. This is essentially multitudes of ontologies and ontology mappings that basically characterizes each individual data set and how it relates to another data set in terms of concepts and their relationships. And we constantly compute more and more ontologies and add to this context to be able to capture and semantically index more and more data. Right now, it has more than 2.5 million concepts that basically characterize every biomedical concept that you can find in a clinical domain or in a hospital system. And then on top of this connected environment, we have all of our artificial intelligence and machine learning, traditional analytics, statistical analytics, as well as more advanced analytics, all tied into the same system through analytic tapestry that can scavenge for the kinds of data that they need and transform them accordingly and create insight that would basically come back to the system. We have also invested in collaboration with Intel to create a federated learning infrastructure to connect systems that use the same ontologies and can basically do federated querying to each other at the runtime and create an environment in which we can learn in a federated environment. This architecture basically underpins all of our software and all of our applications that we are now currently building in Montefiore. David mentioned a lot of layers of onions for a data-centric architecture. As you can see, our architecture also have a lot of those onions. We have a lot of infrastructure to do natural language processing and turning basically linear text, clinical text, into a graph representation that can be connected to the rest of the information that are coming from structured sources. We have master entity identification framework where we can, across multiple sources of data, can identify entities and uniformly generate identifiers for all of them, so we can benefit from the data integration facilities that we can have. We have integrated our platform to a fully integrated communication infrastructure using RTC protocol, so we can have a bi-directional communication supported by this infrastructure and record and basically drive conversations with patients using some of the analytics that we built and so forth. As I mentioned, our Hyperstore is a multimodal database which is semantically indexed and connected through our knowledge graph, so we can consume varieties of data in large file formats or small large formats, index them and connect them and query them in a federated query fashion. And on top of that, we have created these applications that currently basically drive not only our analytic work in Montefiore, but also a lot of the operational works. Right now, one of the applications that we are building is a patient companion application that is using this total understanding of the patient from all of the sources, all of the analytics that are running in Montefiore, no matter who built the analytics, what department or research project was building the analytics. Everything that we know about the patient creates this representation that is available to this app. And this app is being built basically to drive post-surgical care management at home, appointment management at home for the patients, and prescription management at home for the patients, so that we can keep the patients at home for most of their care needs and avoid them to come to emergency rooms or basically spend a long time in outpatient or inpatient clinics. But if they need to come to a clinic, to a professional visit, or to be hospitalized, we are building these application processes to coordinate their showing up in our outpatient clinics, with matching them to the right doctor, with bundling their appointments so that when they come to the hospital, they can be seen in one day and across multiple care services. And when they go back, we have learned a lot. Every single interaction that we had made with these patients within our clinical systems gets recorded and now is available to that app to drive more care. We are using this integrated telecommunication infrastructure that we've built into our app to also automate and coordinate our patient experience and our call center operations. rather than patients spending a lot of time behind the phone trying to navigate the automated messaging infrastructure. Now the system, by knowing what the patients need, who they are, who their care coordinating teams are, where they were before, where they may be able to, they may go, and what care processes they are involved in. We are creating these smart routing so patients can be managed in terms of their communication needs with the hospital a lot more smartly. We have extensive modeling going on in terms of predictive modeling and clinical decision support in patient settings that I'll talk about them about the managed respiratory failure, spinal cancer detection, manage clinical deterioration, identifying patients that may be at risk of dying in hospital, and so forth, that are all running in our inpatient setting, and a lot of care coordination applications in terms of managing social services for patients, managing financial services, pain management, prescription management, appointments. All of those back office coordination tasks are all being managed by this system. But the key about these downstream functionalities are that they are all using the same model. One reference model, one data system that wasn't even aware of these downstream use cases that will evolve over time when we created it. This was 7 years in the making. The very first application that we built around this was a respiratory failure model back in 2017. That was designed to essentially help our critical care coordination teams to identify patients that will need mechanical ventilation 48 hours in advance. This was the very first use case that we intended to support by this infrastructure. Building a call center or having conversational AI at home to manage patients' appointment management was not even in our psyche. We did not even know that there will be such an application. We incrementally built these new applications on top of the same infrastructure, the same data infrastructure. We have not added more pipelines or more software. It is the same software, the same federated queries. We have added a lot of extensions to our existing models to specialize them on understanding the difference between a tumor in the spine and sepsis when it comes to querying data. But there is really nothing that we have written custom into our data architecture to drive these applications. And the second nature of our applications is that every single one of them is aware of others. They know about what is going on in other applications. When there is a new piece of information generated by one application, it immediately becomes discoverable and available to all other applications. And if there is a relevance, if there is a real functionality that it can support, we now are able to leverage all of that information. So how this helped us during COVID-19 pandemic? This is the true test of the stress test of the system that we really needed to turn everything that we had around to become a pandemic management system for us, literally in overnight. And what we could accomplish was that we could create an entire suite of predictive monitoring system for Montefiore in less than 5 weeks, with full-blown monitoring system, both in monitoring the entire hospital, room by room, bed by bed, in identifying patients that are at highest risk of respiratory failure or clinical deterioration, multi-organ failure that was going on, need for ventilation, and not only cast that network of monitoring across the health system, but also monitor each individual patients individually, in hourly basis, and build projection models. And these are models that currently are being shared with our leadership in a daily basis based on trends analysis and forecasting how many patients of what kind in terms of COVID we will see in different facilities in Montefiore 2 to 3 weeks in advance. This was almost impossible to even create a plan in the time that it took for us to build an entire system if we were using any other architecture. We did not have data designers, database managers, ETL writers, stored procedure writers. We did not have any of those functions necessary. It just was straightforward querying and creating pipelines that would generate the analysis that we needed and push it to visualizations that we needed without having to think about what the data model should look like, what the queries should look like. Some of the models that we could build, I'll just very quickly pass through it. In less than 4 or 5 weeks, we built, validated, and implemented. We're reflecting on our ability to accurately identify patients that would need mechanical ventilation and do it in timely enough to be able to do clinical interventions. Up to 32 hours in advance, we could identify those patients. And these are some of the results in terms of what was the impact of these algorithms across Montefiore Medical System in those 3 hospitals that we went live with. In terms of patient mortality, a reduction on respiratory failure, you can see we reduced patient deaths. We reduced significantly the respiratory failure. We reduced the number of days that patients stayed in the hospital during this period. And those days that they stayed in the hospital, we increased the ventilation-free days for our patients. Which this is all based on randomization that we made to make sure that the results that we saw are directly attributable to use of the decision support systems and the analytics that we ran and not other interventions. So we have basically adjusted for all other interventions that were going on in the same period when we were collecting this data. So these are all results that are directly attributable to running these applications and analytics during the COVID pandemic. So I stop here, and maybe I'll stop here and entertain some questions if there are any.
There you are, Michael.
Yeah, a question about your connection between your semantic models, the ontologies, if you like, and the models required to do deep AI. Is there a tight link, or are the deep learning models somewhat disconnected from the ontology semantic models?
No, we have a layer of data transformation. We call it FDL, Federated Data Layer. Its job is to basically connect to the ontology and do all of the federated querying and transformations that are necessary for downstream analytics. So it is mediated by this layer, and that layer's job is just to automate querying and federation across multiple data sets. And it is all configuration and model based. We don't write queries ourselves based on the configurations that we need. It basically formulates the query and distributes it across the hyperstore sources to find whatever input data is necessary for the AI algorithms, and do all of the transformations necessary to create either the temporal sequencing or however the AI layer requires data to be transformed, all in one chunk.
Thank you.
Our AI layer has two essential components. One is this federated data layer. That's essentially about federation of the queries, data integration and harmonization and transformation. The second one is about model development and training and validation of the models, which basically uses this to be able to train and validate the models. And once we have a validated model, it basically switches into an inference and deploys it in basically operational systems. So we cut the cost of deploying new models because we use the same infrastructure to build and train the model as we are going to need to deploy them in our real-time setting.
Great. I'm going to go ahead and hand the mic to our next question here from Sandra Nunn.
I wanted to ask what your electronic health records are, and if all of your data comes from structured sources rather than document systems or something like that. Are they all from structured data systems, clinical systems?
Some of them are, structural clinical data systems are a misnomer. If you look into Epic, yes, there is a structure, but the field itself that has that structured data is unstructured because it doesn't have any mapping to any specific code, or it is just a free text that somebody has put in. And there are a lot of blobs of text that is coming as a part of the structure that you need to understand. And there is no uniformity between how a concept is represented in one part of the EMR versus the other one. So there is that heterogeneity in that source that we need to deal with when it comes, and it is a semi-structured because it has a lot of textual input that you need to also reconcile. Some of our data sources are coming from our PAC system that have their own metadata systems to basically characterize images. They are also semi-structured. Our care coordination data sets are all unstructured, mostly text data, which is basically narratives or notes taken by care coordinators that we need to bring in. We do a lot of image processing. Those images are essentially an unstructured data set that needs to be feature extracted, feature engineered. And we integrate those engineered features into our analytic tapestry. So it is a heterogeneous, what we call it is a multimodal data set. And that tells you why our hyperstore is also multimodal and not just a massive scale graph store, because we have all kinds of data. We have JSONs that we always turn into JSON LD. We basically enrich our JSONs with a lot of URIs that makes them semantically linked to our semantic indexing engine. And we have other like Elasticsearch for being able to do much more faster search on large data sets that are textual and so forth.
Thank you.
Okay, our next hand, Leonard Chikuzo. Go ahead.
You might have a question about how you might have reused available resources. So from my experience, like the stuff in the Obo Foundry is kind of too large to be useful. But what about the stuff the NIH provides, like UMLS for their crosswalks between codes? Did you for natural language processing, do you use CTAKes?
Absolutely. Very good question. Very good question. So when I said we have an ontology of more than 2.5 million biomedical concepts, you would imagine that we didn't really sit down and build an ontology with 2.5 million concepts. What we have done is we have a transformer that we basically created almost 12 years ago, more than a decade ago, that consumes entirety of the UMLS and turns it into simple knowledge organization system, which is an OWL RDF-based representation of meta-theory and data dictionaries with all of their cross-mapping. We have also consumed Odyssey ontology, Athena. I'm not sure if you're familiar with it or not, which it's a collaborative across hundreds of academic medical centers that have created this meta-theory of multiple standard-based ontologies mapped to each other and curated. We have consumed these two into one simple knowledge organization mesh and integrated them. On top of that, we have our own little ontologies that are essentially specializations for things Montefiore. Things that are either experimental or too specific to the way things are done at Montefiore and have no bearing on standards or on larger operations and are localized to a department and so forth. They are linked to this, and they're all based on SKOS, Simple Knowledge Organization System. All other applications use this as their harmonization and integration framework to reconcile their data and map their data, including our natural language processing, which uses CTAKes. CTAKes, as you know, it's a UEMA-based framework, and it's a really good way of building your analytic engines. What we have done is basically taken over the code base, and we generate our own JSON LDs. When every analytic engine that CTAKes has that we use basically produce a JSON LD with proper mappings to UMLS concepts and to our own ontology with those proper URIs, so they integrate directly to our data universe.
Great, thanks. And being from Buffalo, did you use basic formal ontology at all?
No, we did not use basic formal ontology. Historically speaking, I'm raised by the RDF OWL community, so BFF was not really in my psyche. I do not know enough to be able to judge, but we just historically were OWL based and we continued based.
Oh, it's difficult. It's difficult to implement with OWL, but it makes for a really nice conceptual framework from which to approach implementing OWL, which is nice. Yeah. I'll let you go at that. Thank you very much. It's an interesting project.
All right, got one more from Ruben. Should be on now. There we are.
Hello.
Yep.
Hi, Parsa. Thank you for the talk. I have a question regarding technology. Can you speak more about the tech stacks that we're using? So from what I understand, the Hyperstore is not a single data store. It's multiple data sources connected together.
Yes.
And so you use Cognopia for the knowledge graph.
Yeah, so our knowledge graph is essentially based on distributed Allegro graph, which is a transactional, distributed transactional triple store. So we can insert, update, and query at the same time. So it becomes almost real time for us to be able to support concurrent pipelines. And because it's distributed the scales, so it has been able to really address our needs for scale and connectivity across multiple data sets. It uses, it serves two functions. It is our essential knowledge graph for maintaining all of our metadata, ontologies, mappings, and indices that we use to tag data, as well as our record locator across this federated infrastructure, so we know which partition of data a single patient's information is, and where else we should go to find the rest of the information if it is not in our graph store, to be able to query all of the patient data. That is essential function that this distributed graph provides, plus all of our analytic tapestry stuff that is organically evolving and dynamically extending thing is in this distributed graph. Systems that generate structured data in a consistent way and in a copious, streaming of the monitoring or labs or things that doesn't change DICOMs and so forth, or unstructured things that we just need to store, go into those other modalities, the JSON store to Elasticsearch and so forth. But we carry the tags and linkages in our semantic indices, so we always know what patient's information is in where and how it can be retrieved when the time comes. Everything is based on Java and Python, but our mobile applications that I'm told uses a language called Rust or something like that. It is something that Signal API is developed based on, and because we're using RTC extensively, I think that's the development language that my team has been building the mobile app. I don't know if I answered.
Yep. Thank you very much. Yeah, that's very informative. Thank you.
Yeah.
Okay, we actually had a question or comment here from Dave. I'm going to bring him back onto the stage. Okay, Dave, you should be back.
Yep, just couldn't unmute there. No, great presentation, Parsa. Excellent. The one thing you kind of slipped over there is just comment a little bit about the scale that you guys are dealing with all, how many patients, how many triples, which I think is an amazing part of the story.
Yeah, the patients are we have 3 million patients.
Right.
So it's a lot, and quite honestly, I don't know the number of triples that we are currently dealing with. The current applications are over hundreds of billions now,
right.
And growing, and we are growing with our data too. I mean, there were days that 2 billion was just an unimaginable number.
Right.
Now we are thinking about trillions and how do we go there and how do you distribute it across multiple data centers, not multiple clusters and so forth. So we are evolving as it goes. We've also learned something, and that is, as long as that you can wrap your head around identity management in a consistent and scalable way, you don't have to maintain everything in graphs.
Right.
Which are expensive to query. They're fantastic to cross connect and create this organic thing, but not everything requires that, right? Yeah. So we can unload some of it to other infrastructure like JSON stores if you can do that identity management consistently across those platforms, and that's where we've been investing to be able to offload as much as possible of things that doesn't have to necessarily be in graph, but still be able to link them, find them, query them, and integrate them on demand. Federation being the key in terms of how do you federate across these things.
Yeah, excellent. So you can, JT, you can take me down. We got another question there from Sandra.
Yep. Okay, Sandra.
Yes. When you were talking about trillions and all that enormous amount of stuff, what I wanted to ask about is, first of all, does your organization have a retention schedule? And also, do you keep a library or something of knowledge graphs you've already built, queries, things like that? Is there or do you have to recreate things every time someone, comes up with something else? I just wondered over time how long all of this is retained.
Yeah, well, we update our knowledge graph quarterly because all of the world around us updates itself. And we have a process for that we go through, we download the original files, we keep track of those things that we override. We also curate those knowledge graphs, not everything that is coming from UMLS or Odyssey, we just accept it as is. So we have a process to make sure that we can bring all of those new concepts in, but also apply our own curations on top of them to create this consistent representation that we can move forward with over time. We have a governance system internally that basically is responsible for maintaining our own local ontologies, those things that we have developed for our internal use cases, and they maintain their own ontologies and how they map to standards or what's their update schedule and so forth. I didn't quite get the retainment question. What did you mean by retainment?
Well,
retiring concepts and so forth.
For instance, well, in terms of, I've spent most of my life in healthcare. In terms of retention and having legacy systems, which is an enormous problem, and I was in charge of content management systems for a while. How long do you? Is there any do you just keep everything? And so
yes, so far, other than biospecimens, meaning tissue that we collect from patients, which we only keep for 20 years, nothing else has a retirement date. Or we have records from 1994 when we first implemented our EMR system. Essentially, they were physician order entry information, and then lab systems we are just carrying forward. All of these data is there. However, we have not brought all of them to the semantic representation to our PAL. The lineage is preserved and is there. We can go back and retrieve data. If a patient comes in that we haven't seen for the past 15 years, but we know that we have some record of that in our legacy systems, we can go grab it and bring it in. I think, if my memory is right, we have started from 2014. So the data that we have currently in PAL goes back till 2014. Although we have in our enterprise data warehouse and other legacy systems data from 1994.
So, and you mentioned a governance group, and who exactly is that group? Is that system-wide?
No, so there is a system-wide governance group, but they don't really care about ontologies and ontologies. There are like 4 people, I think, one from our research organization, one from pathology that basically deals with the labs and all of those pathology reports, one from our care coordination and care management system, and our BI team.
Okay, so there isn't a chief information governance person or something across the system?
No, there is no chief data and analysis. Well, you can say that I personally operate as that function, but that's not a formal position that we have in the institution.
Okay.
That understanding, that organizational understanding of what it takes to become a data-centric organization is also evolving. It starts with, getting some proof of concepts and then showing value, and then organization starts slowly moving towards that. And we are in that cultural shift position right now, that they see, okay, we actually went on and created data.montefiore.org just to basically represent that there is this notion that data is the prime business of Montefiore, and this is where you go to see Montefiore's data, and so forth.
Thank you.
Thank you.
Thank you so much, Parsa. That was very, very intriguing. I'm certain that everybody understands patient experience, or they will at some time in their lifetime. So, putting it all together in the same reference model is a dynamic way of being able to see all that.
Well, thank you very much. Thank you for the invitation.